Hello everyone, welcome to another lesson, and we are going to cover properties of Boolean algebra today. So it's a good idea to start talking about the properties by talking about things that we already are familiar with. So the first thing it says here is in regular algebra, expressions can be simplified. So we have this expression here, we can see some like terms, for example, 2x squared, we have 3x squared. We know that they can be simplified down into 5x squared, one term instead of two terms. And we can also do the same thing for our x's. 2x's and 7x's give us 9x's, and then of course the 2's stay where they are. So you might not think about this lately, about being simplifying, you just kind of think of it as like terms. But think of it this way. We have an expression in the beginning with 5 terms, and in the end we ended up with 3 terms. So I'll say it's less operations. That's a good thing when we're dealing with computers, because the less we give a computer to do, the faster it can do it. The less steps we give a computer, the faster it can do it. I mean, if a computer can do, let's just say it can do 10 things a second, then less operations is better. You can do those operations quicker. You can run the program quicker. Of course, computers can do billions of operations a second, but the same logic applies. Less steps means you get more done. So it's extremely important that we can take big expressions and make it as small as possible to make our lives easier later and speed up run times and things for computer code. So most expressions can be made into smaller equivalent expressions. So the most important thing, it's not just important to make expressions smaller, you also of course have to make them equivalent. They have to be the same as the original expression, or else you're kind of really not doing a great job. The whole idea is to make them simpler but the same as what they were originally. So expressions in Boolean algebra can also be simplified, but some of the rules are unique to Boolean. So just like regular algebra has its own things, we've obviously seen that Boolean algebra has its own situations like and or. Well, there are some rules for simplifying that we've never seen before, and you've probably never seen before. So we're going to be going through all of those properties in this video. Finally, as Boolean expressions represent logic circuits and networks, as we've seen earlier, it's important that we explore the properties of Boolean algebra so we can make the networks as simple as possible. And this has a direct correlation to computer coding, digital logic, all this kind of thing. You can make a giant network that is actually the same as a network with just a couple logic gates, for example. So we want to try and pick apart these networks and make them as small and elegant as we can, so that if we were to ever implement that logic to make a computer program, for example, it would be nice and optimized. So this is our table giving us 4 of the properties of Boolean algebra. It turns out we're actually going to be covering 9 properties. So let's get started here. The first property should look familiar. Commutative, that's something that you've hopefully heard before, or it works in regular numbers. It says that A plus B, so A or B, is the same as, remember that plus is or, is the same that as B or A. And it just means that we can switch the positions with very little problem, okay? Same exact thing for our multiply, which is and. They can switch positions. So let's look at it in terms of 1s and 0s. How to remember it? Well, sorry, I guess it's not 1s and 0s. 1 plus 2 is the exact same thing as 2 plus 1. So the order doesn't matter when you're adding things. Or in this case, it's also an or. Order doesn't matter for or. It also doesn't matter for multiply, so I guess I should put this down in the middle. It applies to both. The order makes no difference. Just like 3 times 4 is the same as 4 times 3, they both give 12. No matter what you do, these are going to work out to be the same. So once again, the order doesn't matter, even in Boolean. So let's just take 2 situations here. For example, A plus B. Well, let's just say that A was 0 and B was 1, just for the sake of argument. You know, that would mean that we'd have 1 plus 0, sorry, be 0 plus 1 because it's a plus b. 0 plus 1, that equals 1. Well, what if we had b plus a? B plus a being, b being 1, a being 0, still works out to 1. Like, there's really no craziness going on here. So we can see that the order makes no difference. I can go one step further and do the AB. Bring it down on the same line. A and B, just say if A was 0, B was 1, that would give us 0. And finally, BA. Man, I can't get my numbers straight today. 1 and 0. I don't need all the brackets. I can probably make it easier for you. 1 dot 0 equals 0. So at the end of the day, these are the same. These are the same because of the commutative property. It doesn't matter where you move them, they end up being the same. So I'm actually going to remove the brackets on this one. Just remind you that you can use a dot for multiply, which also means and, right? 0 and 1, you need both of them to be 1, so it gives you 0 in the end. Don't forget that these are all logic ideas. Let's go to associative. So commutative means we can move them around, and it makes no difference. Associative means we can make new associations, and it doesn't matter. So A plus B plus C is the same as A plus B plus C, right? Can move the brackets. So grouping, I'll write that in a better grouping doesn't change result for addition and multiply, or for or and. All right, the grouping makes no difference. Just like in this case, A times BC is the same as A times B times C. It makes no difference at all. So how to remember it? Well, remember that 1 plus 2 plus 3, 1 plus 2 plus 3, no matter what way you slice it, that's going to give 6. Same thing as here, 4 times 5 times 6, no matter what way you do that, is going to be 120. So once again, the bracket, the grouping doesn't matter. Doesn't matter for plus and multiply, as long as it's all plus and all multiply. Once you start mixing things together, things get a little bit more squiddly. Okay, so the same case applies. Those are pretty straightforward. I don't need to give extra examples for that. Identity, you can see that something plus 0 is itself, something times 1 is itself. Well, that should be pretty clear from regular algebra. Any number plus 0 gives back the same number. So for example, 2 plus 0 equals 2. That shouldn't be too much of a surprise. And then any number times 1 gives the same number. So 7 times 1 still gives 7. So the same rules apply in Boolean algebra. So let's just say let A equals 1. Okay? And let B equals 0. So we can say A plus 1, we'll try B plus 1, we'll try A times 0 and B times 0. Wait a second, let me double check what I'm doing. I'm doing plus 0 and times 1, my bad. Plus 0 and times 1. So we have plus 0, we have times 1. Let's see what it does. So if A is 1, it'd be 1 plus 0, which gives back 1. Okay. That's to be expected, really. It gives back itself. B. If B is 0, anything plus 0, it'll give back itself. What about the other situation here? A times 1. Well, 1 times 1 gives 1, which is again itself. And then B times 1, well, even if it's 0 times 1, it gives back 0, which is what we started with. So at the end of the day, this is called the identity property because you get back what you started with. The number remains the same. It still keeps its identity. You know? It doesn't change its identity. It stays who it is. Okay? So it's like superhero property. You can be Peter Parker and, you add 0. You change your costume, but you're still Peter Parker underneath all that. I don't know. That was a random reference. Sorry for that. Anyway, add 0. It just gives you back the original. Times 1 gives you back the original. The 0 and 1 property down here. Something times 0 is 0, and something plus 1 is 1. Well, this first situation here should be logical in any case. I mean, you know that that's true from regular algebra, but the second one is a little tricky. So something plus 1 is 1. But let's remember that this plus in Boolean actually means or. So this, I'd say, is our first kind of tricky one. Plus means or. So no matter if you have a 0 or a 1, if you add 1 to it, you're going to get 1 back. So it says how to remember it here. Anything and false is false. So anything, A, and false. So and times 0. False is 0. It's going to be false because you need a 1 and a 1 to be 1. So if it's 1 and 0 or 0 and 0, they both give 0. So take some time to think through that. Think back to your truth tables and make sure that you understand why that's true. Let's do the second case, anything or true. So anything, for example, A, or we can think B, anything. It could be 1 or 0. If we add 1 to it, 0 plus 1 in Boolean is 1. 1 plus 1 in Boolean is still 1. No matter what, we're going to get 1. Okay, so the whole idea here is if we have anything added to 1, it could be the craziest expression in the world, we're going to get 1. If we multiply it by 0, we're going to get back 0. So let me give you a few examples here. Let's just say we had A, B, C, D, E, F, G, H. We could have the whole alphabet here. And these are all 1s and 0s, 1s and 0s, 1s and 0s. If you stick a 0 in there anywhere, it's going to delete the whole expression, okay? It's as if it was never there. You got a 0 here with a multiply, it's going to give you 0, just like regular algebra. But the really cool thing about Boolean is that it simplifies so easy when you add 1 too. So you could have A plus B plus C, D, E, and these are all 1s and 0s and all kinds of crazy stuff. It doesn't matter what you have. If there's a 1 in here somewhere, so let's just say I put a 1 right in the middle. Okay? We see this plus 1. There's a 1 in there, which means it's something or something or something or 1 or something else. Remember, or 1 means that we'll spit out a 1. So no matter what, if there's a 1 in here, something or 1, you're going to get it. Let me make a little picture for that. Let's just say you have an OR gate. Okay, we've got our OR situation. We've got a bunch of inputs coming in. All we need is for one of those inputs to be true to spit out a true, correct? So let's just say we have A, B, 1, C, and D. Well, this 1 will come through on this wire. It's going to go into the OR gate. It's A or B or 1, right? So A or B or 1 or C or D. All it needed was to have one single truth value come through, one single 1, for this to spit out a 1. Okay, so hopefully it makes some sense. At the end of the day, if you add a 1 to any expression, you're going to get 1 as your final answer. So you can see that large expressions can be simplified if you understand your rules. And you'll see where I'm going with this. If you peek ahead in the notes, you can see where we're going to end up with this. But I'm trying to keep it simple for now and help you understand why these things are true. Remember, this isn't regular algebra. This is Boolean algebra. It has its own rules. Let's move on to a few more properties. First here, or at least number 5, is distributive, which one version of this exists in its entirety in regular algebra. A times B, A times C. A in the brackets, sorry, a value outside the brackets, or a variable, a constant, anything outside the brackets, multiplies through, which gives you A times B plus A times C. So that's exactly like regular algebra. So for example, let's just look at the first one. If we had 2 times 3x, that would give 6x, right? 2 times 3x is 6x. And then 2 times 4 is positive 8. So that should be very clear as to why that's true. The weird one here, which it has its own proof, but I'm not going to get into it in this course, is that almost like an opposite version is true. If we have a plus bc, we have a very weird situation going on. You take the a, and you'll place it at the beginning of the brackets, almost like FOIL. I probably don't need 2 of these. And then the b will go in the first bracket at the end, and then the c will go in the second bracket at the end. Okay, so it kind of looks like this. Now, I don't think all those are helpful, so I'm actually I'll keep it there. And if you want to, you can write down a similar diagram, or you can maybe not write it down. It's up to you whether or not you feel that that's helpful. But yeah, I'm going to erase all that extra bit. Maybe I'll try to make a simplified diagram. So here we have A and A. The B, BC, they come at the end here. So remember, they'll come at the end in the brackets as well. Okay, there's only so many ways for me to write that. Hopefully you can make some sort of sense of it as to what's going on here. It'll make more sense the more that we use the property. Okay, but it's called the distributive property because you're distributing the values across the equal sign, in a sense, or across the brackets. The next property, idempotent. My screen took a second to load up. Idempotent is that if you add something to itself, you'll just get back itself, or you multiply by itself, it'll get back itself. And this is a special property that only works in Boolean, or I'll say only exists in Boolean algebra. So it's kind of neat, and the reason it works is because we're constrained to 1s and 0s. So we can think of it without any writing. I'll do some examples after, but 1 plus 1, well, it caps out at 1, so it has to be itself. If this was 0 plus 0, it would also be 0, because of course 0 plus 0 is 0. If this is 1, then this must also be 1, because they're the same letter. So 1 times 1 is 1, and then 0 times 0 is 0. So if you think about it logically, if you use some like test values, this should make some sort of sense. So let me formalize it here. These are all our possible cases, okay? In this case here, a equals, a would equal 0. Sorry, I can't get my fonts right today. A would equal 0. If a is 0, 0 plus 0 is 0. If a is 1, 1 plus 1 is 1. So for both of these cases below, these are the values we're testing. And you can see that in every single case it's true. This is all the possible cases. So in itself, that should make some sort of sense. Let me just add in as a reminder. A plus A equals A times A, or AA equals. Right? That's what we're dealing with in these cases. But the really interesting thing about this property is that it can extend to many, many, many sets of the same Boolean expression. So for example, A plus A plus A plus A plus A. And you could add them all day. As long as you're adding the same thing to itself, kind of all the extras cancel. Because they're useless. There's no reason to add them. A or A, well of course they're all A. You must get A in the end. So that should be fairly clear. What if we had A times 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 A? You can multiply all day as long as it's all A. Once again, it's almost like the extras are shaved off. Because 1 and 1 and 1 and 1 are A and A. Of course, as long as you have the same letter. That's not going to change the value. So there's other cases. What if you had A plus BB plus C plus DDD? Well, again, the extras are always shaved off. So A and A and A give A. B and B is actually the same as saying B. C is just C. And then finally, DDD oops, DDD, King DDD, if you play Smash Bros. ABCD. That's it. You've simplified. So instead of having a 3-termed expression, a 2-termed expression, another 3-term, all added together, you've simplified it drastically. And if these are all separate logic gates, this and this and this, instead of having 2 gates, you have no gate. So it makes a big difference. And then what's another example? We have, let's see, A plus AA plus AAA. Well, all the A's would turn into, this. You could think of it as A plus A plus A, because all the duplicates are removed. And that would be still A, because each of those deletes itself. Or you could think of it as factoring out a common factor. So we could have, you have an A here, an A here, and an A here. That could factor to the outside, giving 1 plus an A remaining plus 2 A's remaining. And then if you remember from a previous rule, 1 plus anything gives a 1. So it's A times 1, and A times 1 is also A. So lots of stuff to chew on here. I recommend that you watch this video a few times if you need to, at least this section, to try and get some understanding or some confidence with why these rules work. So that's our idempotent property. We've only got a few more left. Complement's really easy. A plus not A is 1, or A times not A is 1. Now let's explore why that is. Well, let's just say, in this case, let A equal 0. Well, if A is 0, it's 0 plus not 0, which is 1. That would be 1. 0 times not 0, so 0 times 1 is going to be 0, and so on. In the second case, it would just be the same thing as let A equal 1, and then what's 1 times plus its complement? It would give 1. So let me show you in a bit clearer way. The rule is A plus not A. We know that needs to be 1 because one of these would have to be 0 at some point. Or in other words, one of them would have to be 1. So let me be clear here. Let A equal 0. Let's take this rule. If A is 0, and we have A plus not A, then A is 0 plus not 0. Let's just say we don't know it's 1. All right, A is 0. Add not 0, so it's 0 plus not 0. That's the same as 0 plus 1, and anything plus 1 in Boolean is 1. So this checks out. What if we let A equal 1? And let's try the same thing. Is it still going to give us 1? Well, it certainly should, because we have 1, and in the other case we have not 1, but we already have this 1. This 1, anything plus 1 is going to give us an expression of 1. So hopefully you can see the logic that bubbles beneath the surface here. It's A plus 0, 1. No matter what, our final answer is going to be 1 if you're adding its complement. And the same logic applies for multiply. You can try that yourself. Okay? 0 times its complement is going to be 0. So that'll come up later, but just try to remember that anything added to its complement is 1 and anything multiplied by its complement is 0 because of the way that the 1s and 0s work together. DeMorgan doesn't have... This is also unique to Boolean, okay? Unique to Boolean. Just like the complement was, I guess. There's not really a... All of these are unique to Boolean. There's no analogous operation in our regular arithmetic. So not A plus B equals not A times B. So I guess the most important thing is that instead of having the bar over the whole top, we are allowed to split. I'm hating that pencil today because it's so small. We're allowed to split the negative and turn it into 2 pieces instead. All right. And the way we're allowed to do that is to change the sign from plus to multiply. There is nothing like that in regular algebra. It just doesn't happen. Okay, so it's something to keep in mind. It only exists in Boolean algebra. It's called DeMorgan's property, and he's a famous mathematician that came up with this property. Notice a similar thing here. We have our bar on top, which means not. We are allowed to split it into two pieces, but only if we change the sign. So this actually has a multiply in between. You can think of this as a times b changes to a plus b. Right? So what does it say? How to remember it? Use DeMorgan's properties. Use DeMorgan's properties to change ands to ors and vice versa. So if you have an and but you want to make it an or, split it up. Use it to split up the not and change the operation between the inputs. Okay. So you can use it to split up expressions if you want to, or recombine them. That's a point that it doesn't really make. So if you had something like not A and not B, you can combine them. You can put them both under one big expression, but you have to change the sign. So that used to be a and operation. Now it can become an or operation because we've kind of cashed it in. We've done what we need to do to get DeMorgan's property working. Or what if it was, well, it doesn't need to be A and B. It could be D and F. What if there was a plus between them, but they are still both separated? You could bring them together, all under one sign, under one roof, but you'd have to change the sign in between them. Let's do the other possible cases. What if you had B and C, and they were added, but they have a bar on top? Well, you'd be able to split them up because they used to be under one roof, and now they're under two roofs, but only if we change the sign between them. Or if we have C and D multiplied, but they're under one roof, we can split them up. We can split them up into two different houses, but you have to change the sign in between them. So it's actually not a difficult law, but it's a new law, and it will take some time for it to sink in, okay? So just let me split up these workings here for later. All right. DeMorgan's principle, DeMorgan's properties. That's what that's called. It's a way of us changing the operation, and sometimes that's useful. Double complement. In other words, a double negation, or a not, gives you back the original expression. So it's like saying, I'm not going to eat an entire bag of chips tonight. What you're really saying is that you are going to eat an entire bag of chips tonight, because you've negated the negation. So double negations bring you back to where you started. For example, if I have not 0, what I really have is I've turned my not into 1. So let me highlight this. That was way too big. My not 0 is my 1, and not 1 is 0. Or my not 1 is 0, and what is not 0 is 1. So you get back what you started. Okay, from 0 we get back 0 if it's double negative. From 1 we get back 1 if it's double negated. Okay, or double complement means the same thing. Or in other words, if you want to see a picture, I probably should have been drawing pictures for more of this, but I wanted to keep it fairly short. If you have a 1, for example, and it goes into a NOT gate, it comes out as a 0, correct? Or I'll draw it like this. It comes out as a 0. If you decide to negate it again for any reason, it's now going to spit out a 1, correct? So it came in as a 1, a true value, came out as a 0, and then when you negate it again, it comes out as a 1. And the exact same principle works for if you had an opposite situation. If you had a 0, it would pop out a 1, which would pop out a 0. And so double complement is just a way to change your value from true to false, if that's something that you're interested in. Cool. That's all our properties. Let's do a few examples to try and make sense of them or try to remember them. This is something I like to do in class with everyone with a discussion, but it's okay. We can just do it this way, and you should try them before I go through them. So I'll do the first one, or I'll talk through the first two, and then you can pause the video. So let's see. Use Boolean properties. That's these 9 properties. There's 9 properties of Boolean algebra, which came on the previous page, previous 2 pages, to simplify each circuit and network. And remember, these are networks under the hood. They look like A, B's, and C's, 1s, and 0s, but we know that in the background here they could be built with logic gates. And state any properties used. So the first one, let's just take a look. This is actually done for us. It's done for us as an example. The first case, it's saying, okay, what if we didn't have this piece here? So what if we didn't know? We would just say, okay, A plus B plus C, what does it equal to? Well, we know that these brackets here, if it's all addition, those brackets could be taken and they could be reassociated with B plus C. So that's called the associative property for addition. So we say it's the associative property, and then we'll just say it's for addition. But you could just write associative property, that would be fine. Or in fact, you could just write associative, and that would be enough. And I would assume that you know what you're talking about for the rest. All right. The next one says DeMorgan. Let's see if we agree. It's got an A bar B. So it's A multiplied by B over one roof. Well, we remember, if you remember, DeMorgan, what it does is it allows us to split the knot, split the complement, as long as we change the sign on the inside. And so we've got DeMorgan's for sure. It's a textbook example of DeMorgan's principle or DeMorgan's property. And that's why it asked you this, or that's why the example said that that was the case. So using this as a template, I recommend that you try, sorry, I'm just trying to get everything on the page. Try these 3 example problems. Pause the video and then try them, see what you get, all right? Just see what you get. Now that you've done that, hopefully you've paused. I'm going to write out what I think the answer is. For the first one, this is definitely associative property, because I can regroup B and C, and I'm just going to write next to it that it's associative property. I need to learn how to spell it. Associative. And what operation is it? Well, there's no pluses here. It's just multiply. And remember, we're allowed to use it because it's all multiply. So I'm going to zoom in here. This is all multiply. Or in other words, all and. In the previous case, it was all or. All right, what about number 2? Number 2 here. We've got 2 things under the same roof. I feel like what it's trying to tell us is we can split them up and change the sign in between. So that is another textbook example of DeMorgan's property. And you can call it DeMorgan property for multiply if you want, but it's really just DeMorgan property. And then 3, this, if you had a case where it was like x outside of y plus z, I feel like you would know that it's xy plus xz. So there's no difference in this case. A times b is ab, even though it's and, you can call it ab, or ac. So a and b or a and c. That is the distributive property for multiply. Or distributive property for and. Let me just quickly sketch the gate for this one. I'll just put it to the side. We know that it's AB plus AC. What does that look like? Well, we would have A, B, and C as inputs. A and B would go into an OR gate, an AND gate. And then A and C would go into an AND gate. So A would come out. There's different ways to do this. You're supposed to like hop over it. A and C would go into an AND gate, and then it would be OR both of those. All right. That would be kind of our final answer. This would be A, B, or AC. And how do we know that? Well, I know the first one was A and B, because these are AND gates. Second one would be A and C. This is an AND gate. It's A and B, and A and C, both going into an OR gate. That's OR. So that's why it's AB or AC. So we've made it more visual. It's easy to do that in gates. It's a lot harder to do this with gates because there's not really an analogous situation when you have that for logic gates. It's much easier to write it like this. It's like, what does a bracket even mean for a logic gate? You know what I mean? So it's much better to know this property so I can build the circuit. All right, take a moment to try these 4 questions. Remember, these don't have 1 and 0 answers necessarily. They are asking you what the property is. And you can look back in the table and check. So the first one, something times 1, you should hopefully know that anything times 1 is itself, and if something is itself, it's the identity property. So remember, identity means you get back itself. Your identity is you. So if you are multiplied by 1, you remain you. I know that sounds crazy, but that's why it's called the identity. It stays what it started as. A plus A. Well, any extras are almost like they don't matter. Because 1 plus 1 is 1. 0 plus 0 is 0. So no matter what, it's going to stay what it started as. That's called the idempotent property. Idempotent, I would pretty much guarantee you haven't seen that before. It would be very unusual for you to see that in a math class. But that's what it means. It just means it remains itself once again. A plus B. How the heck are we going to simplify that? Well, we can't simplify it, but we can rearrange. You can put the B first and reassociate. Sorry, this is... yeah, it's called the commutative property. I was going to say it was the associative, but it's not. Commute means to move from one place to another. So just like if you're on a bus and you take the commute from your home to the college, for example, I know, or like a high school, if there were still buses running right now in COVID. Anyway, commute means to move from one place to another. You take your daily commute to work, or you take your daily commute to university or college. Whatever, you're moving from one place to another. So A has moved to there, A has moved there, and B has moved there. But at the end of the day, it doesn't matter if you're going to or from work. It's the same operation being done. All right, what about complement? Well, not A times A has got to be 0, because one of these must be 0. Okay, think about it. If Boolean only deals with 2 things, 1 and 0, if you have something times the complement of itself, somewhere in there you have to have 0. So you're multiplying by 0, which means you get 0 as the answer for this no matter what. And this is the complement property. So you can just call it complement if you want, if that's all you want to write on the page. There's really no reason to overcomplicate that. And then here, the last one, anything plus 1 is 1. That one's nice. That's just what we call the property of 1. So I like you to keep track of the properties you're using, but sometimes, you know, you don't need to always show me every single piece. It's enough if you understand what they are and how they're used. You don't always need to know what the name is to be able to recognize how to use it. Okay, and that's all we're going to cover in today's video. The next section is simplification of networks. We're going to be using these properties in longer examples. For example, we'll be given something like this. We have to use our properties to try and make that more simple or rearrange it, and then we can make a picture from it. All right, so that's for another day. I hope you enjoyed this video. I hope it made some sense, and I'll see you soon.